So good morning, everyone. Good afternoon, possibly evening. My name is Jillian Lennartz. I'd like to start my keynote today by thanking the team at Metal Tech Alley for hosting this conference. As they and the residents of the trail community know, the intersection of raw materials, technology, and the circular economy is essential to a sustainable future. Gathering us all together during this conference is a great step in sharing our ideas and further developing a vision of a sustainable tomorrow. Before I begin, though, I'd like to direct your attention to this cautionary statement on forward-looking information. Today, I'll be discussing some of the academic models of future metal demand, and inherent in models and predictions are some degree of uncertainty. So this must be taken with a degree of caution. Today, I'll begin with a brief introduction to my experience in manufacturing and frame of how parts manufacturers are already intimately familiar with the concept of the circular economy. Then I'll give a quick course in recycling, how metals pose entirely different opportunities for recycling as compared to other products like metal and plastic. Then I'll explore the capacity for recycled materials to meet future demand for metals. And finally, I'll share a holistic model for circularity and the tag team approach that mining and manufacturing can take to make this model possible. All right, so let's begin. Those of you who have reviewed the biographies for the conference know who I am, that my background is in environmental science, and I now work for Tech Resources, leading their sustainability reporting team. However, one thing not included in my biography is my background before I became a researcher and communicator. To be fair, this isn't something usually included in any of my speaking engagements. So why am I showing coins? I come from a family of engineers and manufacturers, people who work with metal for a living. My grandfather worked for years in jewelry manufacturing, working his way up to CEO for Robbins, which made commemorative coins to send to the moon on NASA missions. These coins here are the coins that were manufactured under his oversight and are now in my father's care. My grandfather eventually left to start his own jewelry company. My parents are similarly entrepreneurs in manufacturing. They own a precision manufacturing facility, working day in and day out with metal, using CNCs, milling machines, lathes, water jets, sheet metal fabricators. And my parents still own and operate that facility where I worked for some years and where my younger brother continues to work full time. This is their business, very colorful, I know. And as a side note and full disclosure, I did work on a CNC machine for a bit while working at the family shop. After I ruined a few $1,000 pieces by forgetting to level the feedstock, they relegated me to office work. And if my father is watching today, I'm sorry, Dad. Anyhow, I guess you can say it's somewhat serendipitous that I ended up working for a company that produces metals for use by people like my family. I work at Tech Resources now. So, my keynote today isn't just me speaking as a representative of tech. I'm standing here speaking as a person who worked her teen years and 20s in a machine shop, a person who has a degree in chemistry and understands the molecular processes behind recycling, a person who has invented and manufactured her own instrument for field research, and a person who's worked for a decade in sustainability and sustainable development and now works for a raw materials producer. All right, so finally getting to the meat of things. When writing today's keynote, I was wondering where would be the best to start. My usual philosophy is to keep it simple. Start at the beginning and go from there. But when you're dealing with a concept like the circular economy, where's the beginning? So I'll start from where I began my business career, in manufacturing. All right, so those of you who have worked in manufacturing are probably familiar with the phrase making chips. I was introduced to the term when working with my father so many years ago. For those of you not familiar with the phrase, I'll explain. When a machined part is being made, it's very similar to sculpting. You begin with a solid block of metal and slowly strip away the parts that you don't need. As the tools work into the metal, spirals and chips of scrap material are peeled away. When the part is complete, you have your finished part and a pile of scrap metal. So the phrase making chips is a tongue-in-cheek term for manufacturing. Instead of saying you're making a part, you're making chips. The finished part is then, jokingly, just a byproduct of the chip making process. And here you can see a CNC machine with the chips flying off as the part is being made. It's an in-joke for machinists, but it's also an interesting way of looking at the whole approach to manufacturing. When you're finished with your parts, you have two valuable products to work with: the final part that you sell to your customer and your scrap metal. I know my parents see their processes this way. They have piles and bins of metal chips around their facility. Machinists shovel chips out of machines regularly, placing them in their appropriate bins for recovery. These chips aren't just leftover scrap, they're valuable products. At regular intervals, another supplier comes by to swap out the bins, paying my family for the material and taking it away for use in making and selling more metal bars and extrusion. For those of you familiar with manufacturing, this isn't news. The chips made as a result of manufacturing are high quality feedstock for reuse in creating more product. This is and has been common practice for some time now. For those of us who are not machinists, chemists, or intimately familiar with manufacturing, I'll fill you in. Metal is a perfect candidate for reuse and recycling, and I'll tell you why. One of the phrases I'll use when referring to metal and the circular economy is that metal is infinitely recyclable. It's true, it really, really is. Now, some of you listening right now might be incredulous. Nothing is infinite. How can this woman be saying metal is infinitely recyclable? Some of you may also be familiar with some aspects of recycling and may know that products like plastic and paper cannot be efficiently recycled and used in the same way as raw materials. So, what makes metals different? It all comes down to chemistry, and I'm going to try not to make this a chemistry lecture. I've done that far too much in my life. So, plastics and paper are just long chains of hydrocarbons. You can think of them as very long molecules made of repeating links, similar to an actual chain. Each one of these repeating links is called a monomer. A fact you might be able to use at trivia night, but I haven't been asked that question to date. Can't imagine why. Many monomers in sequence are called a polymer, which is a word you may have heard of. Here you can see the two alternatives to metal that I'll be speaking about, and you can see those repeating links. In the case of plastics on the right, it's chains of hydrogen and carbon that are usually created from fossil fuel products. And in the case of paper on the left, it's cellulose. In the case of paper recycling, we shred the used product, add it to solvents to create a slurry, heat it up, and put it through processes like de-inking, bleaching, and straining before forming it into recycled paper products. This process breaks the bonds between the monomer links in the chains here, where I've put red slashes. This keeps cutting the cellulose fiber shorter and shorter with every cycle of recycling. In the lower blown up diagram, you can see where these breaks are more likely to happen, at the links between each of the monomer segments. In practice, this ends up breaking up the very long fibers that make up paper. Eventually, the cellulose strands are too short and too weak to be useful in paper anymore. The common statistic around this is that paper can only be recycled 7 times before this occurs. Similarly, plastic recycling breaks down over time. There are 2 ways to recycle plastics: the mechanical recycling that involves shredding and melting the plastic, which degrades the product over time, and the chemical recycling process that breaks the plastics down into their individual monomers, the single links in the plastic chain, which can then be reassembled into the final product. The latter has more promise for circularity, but it isn't at the same scale needed to be effective. As it stands right now, plastic degradation with recycling means that plastics aren't entirely recyclable. You can see the issue is very similar to paper, where the chains can break as you heat and process the product. There are many different types of plastics, but they are similar to paper in structure. The same chains of repeating hydrocarbon links or segments, the monomers. Here I have high density polyethylene, HDPE, or a plastic number 2 if you look at the little recycling symbol. It's what makes up products like shampoo bottles. It's one of the best candidates for recycling, but depending on the specific process, it can also degrade. So, What makes metal different? Well, metal is an element, or in the case of alloys, a mix of elements. Unless you're performing nuclear fusion or fission, you're not going to change one element to another. I know alchemists back in the Middle Ages may have tried to, no way to do so. If you melt a metal and let it re-solidify, you still have that same metal. There's no degradation to the properties of the metal atoms themselves. All right, I'll take a quick break here for some mind-blowing facts about metal recycling. Steel and iron are the most recycled materials in the world. This is because of the opportunity to recover large structures like buildings and how easy it is to reprocess the metals. The single most recycled product in the world is the aluminum can. Recycling a single aluminum can saves enough energy to power a 100-watt light bulb for nearly 4 hours. Metals recycling, crazy stuff. So that's all very encouraging for the circular economy. To recap, we can take the scrap from manufacturing, bend that waste stream into a profitable feedstock for a circular economy. Similarly, we can recapture the final products when they're at the end of life and recycle them into feedstock instead of disposing them, and not lose any material quality. Steel manufacturers are even looking at ways to ensure those final products are easily and enthusiastically recaptured after use. As you can see here, the circular economy gets a little more complex, but also more effective. So why would we ever need more metals? Now, this is where my mining and raw materials production cap gets put on, because we do still need mining, and badly, if we're to enable a sustainable future. There are grand limitations to the circular economy model if we truly aim for it to exist as a closed system as portrayed here. The primary issue boils down to supply and demand, as many things in economics do. For today, I'll focus on a single metal product initially, for the sake of time and simplicity. And that metal is copper. This is one of my absolute favorite photographs of a copper product. I guess that's a bit of a weird favorite to have, but here we are. This is a part of an electric motor. An electric motor is made of a stationary tube called a stator and a rotating central portion called a rotor that sits inside the stator. Easy names there. Rotor rotates, stator is stationary. The image here is of a stator, which contains a significant amount of copper since it needs to be electrically conductive. As you can imagine, copper is a very important material for the future of technology and our move toward decarbonization. As I did earlier, I'll pause to share some fast facts. First, known worldwide copper resources are estimated at 5.8 trillion pounds, of which only about 0.7 trillion pounds, or 12%, have been mined throughout human history. Nearly all of that mined copper is still in circulation due to copper's higher recycling rate really, than any other engineering material. In the US, every year, almost as much produced copper is recovered from recycled scrap as is derived from raw mined materials. According to the USGS, global copper reserves are at about 830 million tons, with an annual copper demand of 28 million tons as of 2019. 28 million tons. About 25% of that demand is covered by use of recycled copper, meaning a demand of about 21 million tons of new mined copper a year. So the short of all of that is that our rate of retiring and recycling copper material isn't sufficient to cover the annual need for copper as a source material, and that looks to only become more true over time. All right. As you're likely aware, our society is rapidly moving toward electrification. Many auto manufacturers have indicated that within the next decade or two, their models will be entirely electric. In some jurisdictions, this is even being mandated. For example, late last year, Quebec mandated that from 2035, all new cars sold in the province must be electric. There's a push toward decarbonization that has more legitimacy than ever, seeking to power our electric vehicles and heat our homes with renewable electricity. global ambition is lining up behind wind and solar energy and the development of battery storage to ensure consistent electric supply. The chart here shows a range of electricity generating technologies and the minerals and metals needed to enable them. The bar height indicates the relative difference in need for these materials as compared to the 2010 global energy mix. As you can see, the most green technologies, those at the far right, wind, solar, hydro, have the highest demand for metals. As we move our grid mix more toward these technologies, metal demand will rise. We can see that here. Every one of these low carbon developments requires some amount of copper. Because of this, researchers and modelers are indicating that our global appetite for copper is going to increase for the foreseeable future. As you can see in this image from a 2018 research paper from scientists in the Netherlands, a majority of use will be in infrastructure, the electrification of our society. I could clearly go on for some time about this. The short of the economic concerns around a pure circular economy is that our society is moving in a direction that is to be metal and minerals intensive in order to solve large-scale issues such as climate change. In the foreseeable future, we absolutely need more raw materials to meet the need for progress. So until now, I've only given the example of copper in detail, but it's far from the only metal in this boat, as you saw in one of the previous slides. Here's another image from a peer-reviewed scientific publication seeking to illustrate the demand for minerals and metals that the technological evolution requires. As you can see, all of the modeled demands for metals will see many-fold increases in demand by 2050. These make sense as neodymium and lithium are used in batteries, copper is used in all sorts of electronics and electricity generation, and iron and zinc are used for steel in wind turbines. And here, you can tell I love graphs, we have another visualization of the increasing predicted need from another research group who analyzed the findings of 88 studies covering demand for 48 total elements. I've selected only a few here. As you can see, there's some variation in the exact predictions, but in general, the need for most metals is thought to be on the rise. So to summarize, the demand for metals and minerals is expected to increase. And recycling metals will be unable to keep up with the sheer amount of need for these materials. Here's a great case report on aluminum predicted through 2050 from World Bank. As you can see, the demand for aluminum is predicted to nearly quadruple. Another study in 2019 by Lebre et al. Estimated a nearly 8-fold increase by mid-century. World Bank has projected that even if 100% of retiring aluminum products are captured and recycled, secondary aluminum, recycled aluminum, would only meet 61% of the estimated demand by 2050. If Lebre is correct about the 8-fold increase, this percentage would be only around 35 to 40%. The difference between secondary aluminum production and projected demand is referred to as a demand gap here. Aluminum serves as only one example of the persistent gap between the supply of recycled metals and the ever-steady increase in demand. According to published research, other metals follow similar patterns. Recall the previous slide with the increased demand curves for a variety of minerals and metals. So, to circle back, pun somewhat intended, this is just one of the reasons why I advocate for an expanded view of circularity, particularly from a mining and manufacturing perspective. We must ensure that we can continue to grow economically, meet the resource needs of future technologies, and ensure that there are resources available for all communities around the globe. Accenture has a fantastic model for this, showing that we need to keep materials in use for as long as possible through manufacturing and smart product design. And there's also an expanded loop to show responsible sourcing of raw materials to continue feeding into the circular economy, allowing for expansion of technological advancement and support of people and the economy. There's also an indication every step of the way that waste streams should be bent back into the mainstream, finding ways to reduce waste and maximize value. You can see that loop off the product and manufacturing for waste as a resource. There's our old friends, the metal chips. Ultimately, this model now looks less like a circle and more of a figure 8, or as I prefer to see it, 2 cogs that fit together to drive a holistic circular system. Let's examine that concept a little more, as we could now recognize that the design and manufacturing sector represents the right side of the system, and responsible sourcing of raw materials represent the left side. Okay, so if as a society we're to move toward a future that balances the needs of people, planet, profit, we're going to need to work in concert to establish circular economy commitments across raw materials and manufacturing cycles. On the raw materials side, mining companies must embed sustainability through all steps of the mining life cycle, from exploration and development to operations, and eventually to end of life and mine closure. I've seen great movement forward in this area among mining companies in general. Teck is a member of multiple industry associations, and conversations over my year-long tenure with the company have notably included participation in circular economy topics. However, these frequently aren't referred to as such. Rather, different organizations use terms like material stewardship or responsible production, though the core ambition is the same. For example, Responsible Steel is currently working on a series of standards to explore the balance between secondary metals and raw metals. Key concerns from steel manufacturers are how to properly credit both the use of recycled material and responsibly sourced material. As I previously discussed, it will be impossible to meet future demand using only recycled material, so responsible sourcing standards must account for both without discouraging one or the other. I've also been participating in discussions with various industry groups about the overlap between the mining and manufacturing cycles in supporting responsible sourcing and the circular economy. The discussion is relatively new and therefore somewhat cursory, but various technologies have already been put on the table as potential options to address the material governance topics of recovery and traceability. At Teck, we have a public sustainability strategy, which consists of 8 strategic themes. These cover a wide variety of topics in areas of environmental and social concern. Only one of these 8 topics is responsible production, which encompasses all aspects listed on the left side of the slide. I'm happy to speak about specific initiatives, projects, or case studies from across our operations against any one of these items if you would like to hear more in the Q&A. For the manufacturing cycle, products will need to be designed with recovery in mind. To meet the circular economy needs, products should be able to stay in circulation for longer and be easily disassembled and recycled when they do reach end of life. Currently, this is not the standard. For example, an average smartphone contains up to 62 different metals, many of which can be difficult to recycle as they're in alloys in very low concentrations. The manufacturing cycle of the circular economy must innovate to create products that are just as useful and powerful as current options, but with recyclability in mind. There are some interesting options already being explored. For example, I'm aware of a really interesting smartphone that is currently available and on the market. If you're also interested, go check out Fairphone, a modular cell phone made in part with recycled materials. It's also repairable and modifiable, so you can upgrade the camera or the battery or the storage as new options become available. I can just see that future products across the board are likely to start following this lead. Now, this isn't a plug for a specific product, but an example of how manufacturers are reconsidering their approach to product design and working within the expectations of a circular economy. There are other innovative approaches to material recovery that I've had the privilege to discuss with various manufacturers. Earlier in my discussion today, I mentioned that steel is one of the most recycled metals in the world, in part because it's used in such large projects like buildings. Steel manufacturers are discussing innovative new ways to approach material recapture. And for this one, I'll flip back a slide briefly. All right, so you can see off to the right here, there's a separate loop with as a service given as an example. This is an approach that some metal manufacturers are examining. For example, some innovative manufacturers are considering leasing the metals out to builders long-term for their projects. Then at the end of the building's life, the metal manufacturer could then be entitled to retrieve that scrap metal for repurposing or recycling. Of course, there are a lot of considerations that must be taken into account for such a thing to work, but the idea itself is really quite interesting. Ultimately, these two cycles do work together. So partnerships and collaboration between mining companies and manufacturers are going to be essential to ensure that the most sustainable future becomes our reality. In doing so, we will ensure a happy, healthy, and prosperous future for all. Again, I'm Jillian Lennartz, and I thank you all for your time today. I'm genuinely looking forward to your questions so we can further expand on some of these topics. Thank you.